Hello, this is this key for quiz 5.1 to 5.3. All right, so here's question one. So we have this balanced equation right here. All right, so it says at a certain time during the titration, the rate of appearance of O2 was 1.0 times 10 to the negative third moles per liter per second. What was the rate of disappearance of MnO4 negative at the same time? All right, so this is from section one where the concept is we want the ratio of the rates to be the same as the ratio of the coefficients in the balanced equation. So if we look at O2, that has a coefficient of 5. We look at MnO4, that has a coefficient of 2. So we need to have that 2 to 5 ratio between the rates of O2 and MnO4. All right, so this is going to be 2/5 the rate of O2, and then we look down here, 2/5 of 1 times 10 to the negative third is going to be letter D, 4 times 10 to the negative fourth. Okay, so that one's letter D. Number two. All right, so we have a kinetics experiment is set up to collect the gas that is generated with a sample of chalk consisting primarily of solid calcium carbonate is added to a solution of ethanoic acid. Ethanoic acid is CH3COOH. The rate of reaction between calcium carbonate and the ethanoic acid is determined by measuring the volume of gas generated at 22 degrees Celsius in 1 atmosphere as a function of time. All right, so all that stuff was just background information. This last sentence, that's what we really have to focus on. Which of the following experimental conditions is most likely to increase the rate of gas production? All right, so this is the other concept from section 5.1, the factors that will increase the rate of a reaction. All right, and there's 4 of them that we covered in that section. So we want to look and see, well, which one is going to cause more collisions and give us a faster reaction rate? All right, so decreasing the volume of ethanoic acid solution used in the experiment. No, that's not going to be it. We want more of the reacting particles. Decreasing concentration. No, we want to increase concentration to have faster reaction. Decreasing the temperature, that has the opposite effect also. We want to increase the temperature to make a reaction go faster. Decreasing the particle size, that's what we're looking for. Decreasing particle size means we're increasing surface area. So we're going to have more collisions with smaller particles. So it's going to be letter D. Question 3 is pretty much the same concept here. We have this figure 1. So this part right here in the middle, that's our magnesium metal, according to the chart over here. These clear, larger circles, those are our chloride ions. And these smaller, darker circles, that's H3O+. Those are hydronium ions. That's what happens when you have an acid in solution. It gives you these hydroniums. So this outside is caused by hydrochloric acid, HCl. That's where that comes from, and it's reacting with magnesium. All right, so in figure 2, we have the same particles, but it just looks like we have smaller particles of magnesium instead of that larger chunk that we had in figure 1. So looking at this, the magnesium here has more surface area, so you would expect this reaction in figure 2 to occur faster. All right, so now we look down at the choices. It's just looking for which of the reactions will initially proceed faster. So we want to look at figure 2, the reaction in figure 2, because more magnesium atoms are exposed to HCl in figure 2 than in figure 1. That's going to be the correct answer right there. D also says figure 2, but it says it has less surface area. That's backwards. It has more surface area than figure 1. So the answer is letter C. All right, when the chemical reaction 2NO plus O2 produces 2NO2 is carried out under certain conditions, the rate of disappearance of NO is 5 times 10 to the negative fifth. This is moles per liter per second, or molarity per second. What is the rate of disappearance of O2 under the same conditions? So again, we want to relate the ratio of coefficients, which is 2 to 1, to the ratio of rates. So we need half of this rate for O2. So it's a 2 to 1 ratio, NO to O2, so we want the 2 to 1 ratio of the rates for NO to O2. So that means the rate of disappearance of oxygen has to be half of this value that's given. So that's going to be 2.5 times 10 to the negative fifth. All right, so we just look at all the values for the rate that are given, we can just focus on those, and this is the only one that has the correct rate. So, and this is talking about 2 moles of, or 2 molecules of NO consumed per molecule of O2. That is the correct ratio right there. So it's letter A is the correct answer. All right, question 5. The initial rate of the data above were obtained for the reaction represented below. What is the experimental rate law for the reaction? So we have this balanced equation. This is the method of initial rates. So we have 2 reactants here, NO and O2. So we want to look at the experiments to figure out what's the order for each reactant. All right, so to evaluate the order of NO, we want to look where NO is changing and O2 is held constant. So that's going to be experiment 1 and 2. And we look at by what factor is it changing. So NO is doubling. It goes from 0.1 to 0.2. And then you look at the rate also doubles. It goes from 2.5 to 5, the same exponent. So if the concentration and the rate are changing by the same factor, that means it's going to be first order with respect to NO. When you figure out the orders, it's usually 0 order, first order, or second order. If it's 0 order, you change the concentration and the rate would stay the same. If it's first order, the change in concentration and the change in rate are the same. Okay, in this case, this doubles, the rate doubles. They're changing by the same factor. That tells you it's first order. If it's second order, that means the rate would change by the square of the rate of change of the concentration. So if this were to double, the rate were to quadruple. Okay, but in this case, it's first order with respect to NO. And then we do the same thing with O2. So we want to look at experiment 2 and 3, where NO is held constant. So in this case, O2 is quadrupling. It's going from 0.1 to 0.4. This is going from 5 times 10 to the negative 4th to 8 times 10 to the negative 3rd. So it's like it's going from 5 to 80. So it's 16 times the rate. So 4 squared equals 16. So the order with respect to O2 has to be 2. So now we look for the rate laws down here, and this is the one that matches up. NO to the first order, O2 to the second order, so the answer is B. All right, question 6 is a similar type problem. We're looking at the method of initial rates. So with this, we have 2 reactants again, A2 and B. So we want to figure out the order with respect to each one of these. So to figure out the order for A2, we want to look at trials 1 and 2, where B is held constant. So A2 is doubling in this case. The rate is doubling. So if they change by the same factor, that means it's going to be first order. So we know it's first order with respect to A2. Now to evaluate B, we want to look at trials 3 and 4, where A2 is held constant, and then we look by the rate of change. So it's going from 0.05 to 0.10. So B is doubling, and the rate also doubles between those 2 trials. So they're changing by the same factor, so that that also is first order with respect to B. So we can just focus on the rate laws, and we want to look first order for A2, first order for B. So the only choice that matches up with that is letter B. All right, question 7. So we have the pure substance X decomposes according to the equation above. Which of the following graphs indicates the rate of decomposition is second order in X? Okay, so this is the section 5.3 with the integrator rate laws. If we have a second order rate law, that means the straight line graph is going to be 1 over the concentration versus time. All right, so now we look at our choices. So that means it has to be D or E. So 1 over the concentration versus time gives you a straight line. Now the difference between this, in D we have a positive slope, and E we have a negative slope. So the other part with this is for a second order integrated rate law, the slope of the graph is going to be equal to K. And K has to be a positive number, so we have to have a positive slope. So we want 1 over the concentration versus time to be a straight line graph, and we want the slope to be positive because that represents k, and k is always a positive number, so it's D for number 7. Okay, and then question 8. If an oxygen isotope O20 has a half-life of 15 seconds, what fraction of a sample of pure O2 remains after 1 minute? All right, so in 1 minute, we have 4 of these 15-second half-lives. So this is going to go through 4 half-lives. So just drawing this out, if we start with just 1, after the first half-life, now that's going to get cut in half. All right. After the second half-life, we're going to lose half of that amount. So now we're going to get cut down to 1/4. After the third half-life, now you're going to be down to 1/8. And after the fourth half-life, you're down to 1/16. Okay. Now another way to look at this, the half-life. Okay, so another way to look at this half-life information, if we want to find our final concentration after a certain amount of half-lives, we would take our initial concentration at time 0, and we'd multiply that by 1/2 to the n being the number of half-lives. So in this case, it'd be 1/2 to the 4th, so that would also give us 1/16. Okay, so after the 4 half-lives, we have 1/16. So now we can go back to our choices, and that's letter E, 1/16. All right, that's the answer there. And that's the end of that quiz, so have a good day.